Lithium, often called white gold, is the fundamental element powering our electric future. From every electric vehicle to the massive battery banks stabilizing solar and wind grids, lithium-ion batteries are the foundation of modern clean energy. Global lithium demand is projected to soar by 8 to 11% every year, potentially increasing 20-fold by 2050. Our supply chain is struggling to keep up, creating a critical shortage. Traditionally, we got lithium in two ways: mining hard rock, which is energy intensive and pollutes the environment, or by using vast, iconic solar evaporation ponds, primarily found in South America's Lithium Triangle. Evaporation sounds easy, but it's painfully slow, taking many months, sometimes years. It uses huge land areas and wastes massive amounts of fresh water to wash the final product. Crucially, it only recovers around 30 to 50% of the lithium. The deeper problem is purity. Lithium exists in brines, salty water from salt lakes or geothermal sources, as a tiny, positively charged ion, Li+. It's swimming in a soup of similar unwanted impurities like sodium, potassium, as well as big bully ions like magnesium. Separating these ions is like trying to find the one smallest marble in a pool full of slightly bigger, identical-looking ones. This challenge is why direct lithium extraction, or DLE, is the necessary revolution. DLE acts as a high-tech molecular filter. DLE methods can capture lithium ions highly selectively in hours, bypassing the need for evaporation. One DLE strategy is size selection, using advanced filters like nanofiltration, NF, or metal organic framework, MOF membranes. NF membranes act like sieves, letting monovalent ions, lithium, sodium, pass while rejecting multivalent ions, calcium, magnesium, and others based on charge and size. Here's the genius twist. The key isn't just the size of the ion, but the size of its water jacket. In liquid brine, every ion is surrounded by a hydration shell. To pass through a tightly controlled nanochannel, like those in advanced MOF membranes, e.g. UIO67, or covalent organic frameworks, COFs, the ion must shed some of that water jacket. Because magnesium holds on to its water molecules more strongly than lithium, it takes more energy for the magnesium to pass through the pore. The membrane selectively favors the ion that requires the lowest dehydration energy barrier. This clever design, using dehydration kinetics, provides selectivities up to 159:1 for lithium versus magnesium in materials like UIO67. But what about sodium? Both lithium and sodium are monovalent, meaning standard filters struggle to separate them apart. This is where we need the most revolutionary idea: the electric superhighway. This tech is borrowed straight from high-end battery research, using solid-state electrolyte materials. These ceramics, like LLTO or LATP, are designed to conduct only lithium ions. Imagine a super-rigid crystal lattice, like an atomic skyscraper with perfectly measured angstrom-scale pathways. When an electric field is applied, the lithium ion migrates by literally hopping through defined vacancy sites in this solid structure. Because the crystalline pathways are so narrow, the bottleneck size is between 1.8 and 2.0 angstroms, they physically exclude the slightly larger sodium ions and prevent water molecules from passing through. This is anhydrous hopping. This transport is controlled by the rigid crystal structure, not chaotic water-filled pores. The selectivity is unparalleled. Researchers have found immeasurably low fluxes for competing ions, achieving lithium-magnesium selectivity factors up to 87,000 and even higher in some lab tests. That perfect selectivity sounds great, but these ceramic SSE materials are historically brittle. You can't run a chemical plant on a fragile disk. The engineering challenge became, how do we make the perfect filter tough enough for industrial scale? researchers started integrating these selective ceramic particles into flexible polymer matrices. For example, the LATP/CA membrane embeds the selective LATP ceramic into cellulose acetate, Ca, a sustainable, biodegradable polymer. They even added polyethylene glycol, or PEG, to increase flexibility. This flexible composite approach delivered the goods. Tests showed magnesium 2+ concentrations reduced by 300-fold, and after a simple two-step electrical separation process, they achieved incredibly high purity, with lithium/sodium selectivity reaching 543:1, all in just 12 hours. This is precision, speed, and sustainability combined. For truly massive scale, manufacturers are adopting layered composite membranes. A recent breakthrough, SLAM membrane architecture, uses a robust ceramic substrate for mechanical support, the selective LLTO layer, and the final hydrophobic polymer layer to seal defects. This design allowed researchers to finally build large-area membranes, a 2,500 centimeter squared sheet, that maintained high performance. This large-scale membrane successfully extracted over 30 milligrams of lithium from 1,000 liters of simulated seawater in a single day, achieving an exceptional lithium-magnesium selectivity of 87,000. We are moving from small lab discs to industrial-sized filter sheets. However, extracting only 30 kilograms of lithium from seawater, which contains only about 0.2 ppm lithium, would require about 1 million tons of seawater. That is a lot of water. The final scientific frontier is efficiency. Traditional electrical separation uses a lot of power, but new systems like redox-electrodialysis, RCE, developed by Stanford researchers, are shattering energy barriers. RCE uses a chemical engine to drive lithium across the superselective membrane with an ultra-low operating voltage, sometimes as low as 0.25 volts. This results in a revolutionary energy efficiency, requiring only 1.1 kilowatt-hour of electricity to extract 1 kilogram of lithium, compared to the thousands of kilowatt-hours required for earlier methods. Other innovative systems, reported by the same group, by leveraging the tremendous osmotic energy created by the concentration difference of chloride ions, can achieve spontaneous lithium extraction. They extract lithium with a net energy output. You are essentially mining lithium and producing electricity simultaneously. This fundamental science has cut the cost target to under $5,000 per ton lithium carbonate. This is the tipping point where DLE shifts from a lab curiosity to a global economic game changer. The scientific breakthroughs are moving the entire industry away from the dusty, slow solar fields to modular, high-tech factories that can be built almost anywhere. This is solving the geopolitical issue of supply concentration. Companies like E3 Lithium in Canada are repurposing legacy infrastructure, extracting lithium from vast oil field-produced brines. They use specialized ion exchange sorbents to snatch lithium from low-concentration brines. Their pilot achieved 99.78% purity battery-grade lithium hydroxide. This proves that resources previously considered waste, like oil field-produced water, can become critical mineral hubs. In Germany, Vulcan Energy Resources is pioneering the integration of DLE with renewable energy. They tap hot geothermal brines in the Upper Rhine Valley. Their DLE process is adsorption-based, and critically, it uses the geothermal heat and electricity to run the extraction. This allows them to project near-zero carbon lithium hydroxide production, securing a supply chain for European automakers like Stellantis. Meanwhile, companies like EnergyX and Lilac Solutions are applying highly selective membranes and ion exchange technology to traditional brines in the lithium triangle. Lilac's proprietary ion exchange beads, proven in Argentina, achieve over 90% recovery, crushing the 30 to 50% efficiency of traditional methods. All these DLE technologies promise a drastically reduced environmental footprint, up to 90% less water consumption compared to evaporation. By recycling or re-injecting the processed brine, they preserve the hydrological balance, making the entire lithium supply chain far more ethical and sustainable. The transition to clean energy hinges on solving a nanoscale puzzle, finding the lightest metal in the saltiest water. We are moving from primitive solar evaporation to an age of molecular engineering, where the science of anhydrous hopping and selective sieving dictates the supply of our future. By perfecting this science, we're not just speeding up production, we're making the production of lithium cheaper, cleaner, and ultimately ensuring that electric vehicles and grid storage are affordable and accessible to everyone. The techno-economic analysis promises costs well under $5,000 per ton lithium. This is the tipping point where DLE shifts from a lab curiosity to a global economic game changer. The story of lithium extraction is still being written, with breakthroughs and startups showing up every day. If you were captivated by the atomic-level science changing our world, please check out the detailed videos posted on this channel about the science and tech of sustainable technologies. Until next time, stay curious.